I'm Joanna. I'm not a maths person. I'm more of a language person, but all sorts of people can do maths. I'm going to demystify the logistic curve, which has got a bit of a strange name, and I'm going to do it using this cool graphing tool called Desmos.com. So I'm going to start off with a curve that I hope you know, e to the x, the exponential curve. It grows really rapidly, really steep curve. And just to remind ourselves, when x is 0 here, this expression e to the x, e to the 0, anything to the 0th power is 1. So this is 0, 1, y is 1. And when x is 1, e to the first power is just e. So we expect here when x is 1, y is e. There we go, which is 2.718 approximately. Cool. Okay, now I'm going to do a little bit of algebraic manipulation over here. I'm going to take the reciprocal of the reciprocal, and the reciprocal of the reciprocal is the thing itself. So that shows that these two expressions are the same. I just wrote it differently. And now I'm going to add a term to the denominator. I'm just going to add a 1 and see what happens. Whoa, check that out. That created a completely different curve, that green curve. I'll do it again. Exponential, you add a 1. It's a totally different curve. So as opposed to the exponential curve in blue, this new curve is not growing unbounded. It's got a bound here. It's getting closer and closer to what looks like 1. And on the left, as x gets more negative, it gets closer and closer to 0. So let's take a look at that curve. We'll just zoom in a little bit. Yeah, so again, when x is 0, we go over to this expression. We put e to the 0 is 1, so that expression is 1 over 1 plus 1, 1 over 2, or a half. So here, when x is 0, y is a half. And then as x gets larger and larger, well, when we make x larger and larger, e to the x gets really, really big. 1 over e to the x will get really, really small, closer to 0. And so this whole expression will get closer to 1 over 1, which it does. And then, you know, when x is really negative, this e to the x when x is negative, that kind of brings e to the x to the numerator in this little term. And that makes this whole expression approach 1 over e to the x, and as x gets really big, this whole thing will approach 1 over a large number, which is 0. So that curve is the logistic curve. Now, why is it called the logistic curve? It's got nothing to do with logistics, actually. It's actually comes from this Greek word logistikos, which means practiced in arithmetic or rational, with the Greek root logos for reason or calculate. Well, the person who gave it that name is a Belgian mathematician called Pierre Francois Verhulst. And in the mid-1830s, he, alongside his supervisor Adolphe Quetelet, was using mathematical functions to model population growth of European countries. And we don't know why he introduced this curve and called it the logistic curve, but he did mention a curve that they were using previously to model populations. So they used to model populations using the exponential curve because populations grow so rapidly, but the exponential curve is not very realistic because populations don't grow unbounded. They actually at some point reach, a bound or a plateau as resources run out. And as he was introducing this curve, well, this wasn't always called the exponential curve. It used to apparently go by the very confusing name of the logarithmic curve, which today is something different. But perhaps in that context where Pierre was introducing a superior function that could better model population growth, he was like, oh, maybe, I'm totally speculating, but maybe he just wanted to have a more serious name and also have a Greek root like logarithm, which also has the Greek root logos. Who knows? Anyway, I think, these days logistic curve is quite confusing. I prefer the name the S curve, which, if you want to make it fancier, like it kind of, it looks like a shallow S, but yeah, the fancy name for S is sigma, so you might also hear this as a sigmoid curve. And S curves are really useful for modeling all sorts of things. So we can model population growth, as we said, where you've got small population, grows exponentially rapidly, but it starts to, get slower and plateau. You can also model product rollouts in markets, like say the introduction or rollout of smartphones. They grow exponentially as everybody hears about them, but then the market gets saturated and it kind of like the purchases plateau. But another phenomenon which we can use these curves to model is a phenomenon that go quickly between the values 0 to 1, like a neuron in a brain. Cool. So, all right, let's say we want to model some of these things like population. How do we use this curve to model population? Like, we need to, first of all, we need to like maybe shift it to the right, because there's no negative values in population, right? So let's try to shift it to the right. Shifting a graph to the right is easy because we just take the x value and we make it whatever the x value was. Say we want to shift it by 10 units before. And there we go, that's shifted it now. Now that midpoint is happening around 10. But this representation is getting a little bit scary to me. I just want to let's go back to what I had and I'm going to do a little bit of algebraic manipulation again just to make it look friendlier. I'm going to multiply top and bottom by e to the x. So the top will be e to the x, and the bottom I multiply each term by e to the x. So this 1 over e to the x is just going to become 1, and this multiplied by e to the x is e to the x. So this expression is the same thing, just a different way of writing it. And okay, again, if I wanted to shift my curve to the right by 10, make the x's be what their x was 10 units ago. There we go. Obviously this is like maybe time. I could change 10 to whatever I wanted. I also want to stretch the graph of the curve vertically because my population isn't going to grow to 1. It's going to grow to like 100 million or something like that. So to stretch it vertically, well, if I think that as when x gets really large, these two terms are kind of the same. This whole expression is going to just be e to the x minus 10 over e to the x minus 10 is 1. So to stretch it out, I can just say I want to stretch it up to 10 as well. I just put a 10 there on the numerator. And now I can see that, it goes from 0 to 10. And again, I can make that 10 million if I'm modeling population. I might also want to be able to change the steepness of this S. Oh yeah, it's looking more like an S now, isn't it? I might want to make it shallower to say that the population is, it's not hitting that, that midway point as quickly, so I'll make it shallower. I just make I can put a factor out in front of the X to make it shallower, so I'll make the 0.5x a bit shallower. If I wanted to make it steeper, I just go the other way. I make it like 2x instead of half x. And now, bang, there's like very, quick explosion to being saturated. Cool. On this point that you can see how we can make the S kind of as sharp as we want. This is, again, really useful for modeling those neurons or those things that quickly change between 0 and 1. I'll just show you that, like, if let's take it back to the original function, and just get rid of all these extra bits here. But, no worries, I can quickly make it again. Plus e to the x, there's my S shape. Okay, and I want to model some behavior, something that goes in between 0 and 1, and I want to make it a sharp S. So I can just change my X to go double as fast, a bit faster. I can make it like 20x. I can make it like 1, I'll do it 1 more. And there, now it's looking like a step function, like this really square off thing. So that's really cool, that's really useful. Great. The last thing that I'm going to show you today is the derivative of this function, or as I call it, the difference function. So how is this function changing as x? Oh wow, look, you can make all sorts of funky little functions just by manipulating different parts of the expression. So yeah, how is this function changing or how is y changing as x changes? I'm going to take the derivative of it, right? So I can already kind of hypothesize here that I could, the change is also the gradient. So here, like, well, you can see right at the ends, the gradient here is horizontal as x gets really large, and also horizontal or 0 as x gets really negative. And in the middle here, we can kind of work it out ourselves by just eyeballing it, if I get the right scale. But that's it. All right, so if I just look at this scale here, I can see that it takes 4 squares from this point to this point. So for the function to increase vertically by 1 unit, it had to travel 4 units across. So the gradient here, rise over run, 1 unit is the rise, 4 units is the run, 1 over 4. The gradient around this point is 1 over 4, or 0.25. We'll keep that in mind as we do the derivative. Doing the derivative, this is a quotient. So you use that quotient rule you have from high school. I'm just going to like use this formula. So we've got a function that's f over g, and then we just do this f dash g dance. So let's try to do this. All right. F is g, so f dash, f is e of x, and the derivative of e of x is e of x, so f dash is e to the x. I'm just going to turn off the graphing while we figure it out. G is the bottom expression, so we've got f dash times g. Okay. Okay, f dash times d minus g dash. So g is that bottom expression, and the derivative of that, well, it's just e to the x. So g dash is e to the x times f, and f is e to the x. So that's my numerator, and then my denominator is g squared, which is that 1 plus e to the x squared. All right, going to clean this up before I graph it. So at the numerator here, I'm going to expand out that, take that e to the x and put it inside. So I'm going to put it in there. I need to put one there too. So now you can see I can just, these terms cancel out, right? So I've just got a e to the x on top. And on the bottom, that's simple enough for me. I'm going to leave it like that. So, graphing time. What do we got here? Ta-da! Ooh, look at this kind of function. This is, again, totally different curve. I'm just going to change it, so let's make it red. All right. So this is like kind of a really like flat bell-shapey thing. But the values should work out, right? So at the ends of the graph, the gradient is approaching 0 at both ends. And in the middle of the graph, when x is 0, we expect the gradient to be 0.25, and that works out. So yeah, that's a pretty funky looking bell-shaped curvy thing from this S-shaped curvy thing, which came from that not, I don't know what kind of shape that is, just a really steep curve. Isn't that fascinating that like you can just play with these exponentials and get really different shapes, and you can, stretch and expand them as you like to model different things. For example, here, if I wanted to, make it more of a mountain, I could, just put a factor out in front of the x. Ooh, it's not quite a mountain, but it's a cool looking thing. Finally, I'm going to finish by just making a point here about, so we've got the logistic curve and its derivative or difference curve, which is this funny bell-shaped thing. Just want to point out, look how similar these expressions are. Like this, if I just, like 1 plus, this denominator, this 1 plus e to the x squared is like having two of them side by side, right? And yeah, so that's still the same thing. And what this actually is, like, if I called this, say, y, made it explicit, y equals that shouldn't have changed anything. Just calling it y. Then I can replace this whole thing with, well, this is kind of e times 1. And this e over 1 plus e to the x part of the expression is y. And this 1 over 1 plus e to the x is actually 1 minus y. If you did the fraction kind of evaluation, you would see that this whole expression is actually y times 1 minus y, which unfortunately, that's not going to graph that for me. But yeah, this kind of, it's called like self-similarity. So anytime you've got a curve with these exponential terms, just like how e to the x, its derivative is just itself, e to the x. So if e to the x was y, the derivative is just y. For this curve that's got a few more e to the x's, in there in different places, and its, sorry, this one, its derivative is almost itself. It's itself times 1 minus itself. And yeah, that's quite cool. So hopefully I've shown you that we don't have to be intimidated by this logistic curve thing. It comes from quite simple expressions, but it quickly kind of gets interesting, yeah, with what you can do with it. So thank you very much. Happy maths.